Hi, in this chapter we are going to talk about integration, so let's get started. First of all, I'm going to talk about the trapezoidal formula. It is a technique for approximating the definite integral. The trapezoidal rule tends to become extremely accurate when periodic functions are integrated over their periods, such as cosine or sine and so on and so forth. The error of the formula depends on the second derivative, such that if the integrand is concave up, it means that the second derivative is greater than 0, so it's positive, then the error is negative and the trapezoidal rule overestimates the true value. On the other hand, if the integrand is concave down, then the error is positive and the trapezoidal rule underestimates the true value. So that's why the second derivative is very important in the numerical analysis of these integrand formulas. So this is the sketch of trapezoidal formula, and if you are familiar with linear interpolation, this is the case here. We are just doing linear interpolation. We have an interval from A to B. We creating subsets. So we divide this A to B interval to as many sections as we want, and of course the more sections we divide this interval, the more accurate our algorithm gets, and do a simple linear approximation, linear interpolation in these subsections. So this is the trapezoidal formula. If you like equation, then this is the exact trapezoidal formula, of course. Let me tell a few words about Simpson formula. It is a bit better. It is a method for numerical integration, of course, the numerical approximation of definite integrals too. Basically, it is a quadratic interpolation. So trapezoidal rule was a linear interpolation. Here we do a quadratic interpolation, which if you are familiar with parabolas, for example, or quadratic functions, we want to approximate or integral with the half of a parabola. The error of the algorithm is proportional to the fourth derivative, and it yields better results than trapezoidal rule. So this is the formula if you like equations, and this is the sketch of Simpson formula. So here we have the A to B interval. We create sub-intervals, and we don't do a linear interpolation. We want to approximate the function with the half of a quadratic function or a parabola. And Monte Carlo integration gets very, very important. It computes a definite integral too. Monte Carlo randomly chooses points at which the integrand is evaluated. It is a non-deterministic approach. And this method is particularly useful for higher dimensional integrals. To be honest, this approach is not so efficient for lower dimension. Lower dimension, you can use trapezoidal rule, you can use Simpson method, but in higher dimension, for example, you have 100 dimension or even more, and it is the case in statistical analysis, for example, or if you want to integrate in higher dimensions, then Monte Carlo is definitely the best. It's very popular technique in finance, in physics, although it's not converging very, very fast, so it's not so accurate, but you have to run it several times. And if you are familiar with and interested in quantitative finance, then lots of models, such as the Black-Scholes model, how to calculate the price of the option, how to create Merton model, and lots of fields in physics and engineering, it's very, very important. So, for example, you want to calculate the area of the circle with the help of Monte Carlo integration, then we can approximate it. We just have to draw a two-dimensional plane. It has a 1 by 1 two-dimensional plane, and we want to approximate the area of the circle with radius 0.5. So we just randomly drop dots to these planes, and we just have to calculate how many dots are inside and how many dots are outside the circle. And we just we can calculate the area of the circle with a simple equation. t over t prime is equals to dots all pair dots inside, where t denotes the area of the square and the t prime is equal to the area of the circle. So we just have to calculate these dots. It will be clear during implementation. Thanks for watching.